the reliability of the engine. And so that you consider a very, very small project in the 777. Now, for this example here, we can see this is 787, but some of us may wonder about why the Boeing spent a lot of money to invest and come up with a new model. And we can see that every one of us, we know about 747 model 400, so that is more than very, very good enough if they can fly. Many fly, direct flight, and many hours during the flight. But for after the 747, for the 757, 767, but also if we are going to looking at for the 777, so every new model, so they do spend a lot, they do invest a lot of money. And we are talking about billion dollars. And the question here, the question here is why they have to spend a lot of money in order to have a new product instead of they already have a good product already. So mainly because the customer we want more all the time, anytime, and every time we want to have more. So that's why a better product. And if we are going to look and say, well, if we have the 777 already now, why again, Boeing spent a lot of money to invest for the 787. So I believe that many of us came here, perhaps also by 777 or maybe 787 also. So I flew here from New York by 777, and mainly the flight was from New York to Beijing, direct flight, and that is 17-hour flight. So we can see how reliable, many products, and including for the airplane. But some of the product you don't have to show how good in terms of the reliability before you deliver the product to the customer. But for example, for the airplane, I know they have to show to the government and how reliable in terms of the reliability to the government before they can deliver the product to the airlines. And they do spend a lot of time to quantify, to looking at, to show how reliability in terms of the whole airplane. And if you are talking about the whole airplane, there are hundreds, thousands of the subsystems, including the electrical power system, engine, landing gear, and many other things. So mainly. In summary, mainly because we all customers, we all the time we want more, and we don't want to pay too much money to buy for the new product. Okay. So another example here, also for the television here, we do see our regular television here for 2 dimensions, but recently, for the last couple of years, we can see 3D television and so on. So, two-dimension television already good enough, but we like to see more. In particular, if you are from the top of the hotel, you want to look down, so you can you want to see very clear, not beside for the 2-dimension but 3-dimension and so on. So this is the same thing. Also, like yesterday, we have a keynote speaker yesterday morning, so talking about smell from the television and so on. So that is also very interesting. So we can see for the next 5 or 10 years. Okay. So in terms of the better product, and better product is one of the indicators in terms of how you can quantify the reliability of the product. So that is the main focus for my talk today. But sometimes we don't know how good the product, and of course it comes from the manufacturer point of view. Every time we are going to produce the new product and deliver to the customer, So we want to consider this is the best we can do, or the best we can produce. And this example very interesting last year in August. And one of the gentlemen played ski outside in the New York City, and mainly played ski and ran out the gas, and then he have no way but have to swim into the Jamaica Bay in New York City, and he need help. So he get into the New York John Kennedy Airport. And then, and the main purpose, because in New York after the September 11 and so on, but they do have a security system, and that system is they spend a lot of money, more than $100 million, and to make sure in terms of the security issue. Okay. But this gentleman here, when he get into the international airport and get into the terminal, so nobody know that. So this is one of the example where we don't have a good, reliable product so far. So in terms of the product process, so this is very long process, and if we are going to look at it from the beginning until the end of the product before going to deliver to the customer. So this is I will go quickly here, mainly in terms of the product specification, being the independent verification and validation. So of course, during the development process, so they are going to go through in terms of the first phase, usually for the customer coming and talk to the manufacturer or the engineer, going to see if they can produce the product. And surely many times when the customer coming and say, well, this is what I want for my product, and I'm willing to pay the money. So many times the manufacturer accept and going to accept the project and working on for the product. In terms of the IVNB, when we do the data mining, data information, and so on, so IVNB is very common because we are going to go through every step and to make sure that it be very certified for specification. So before we are going to deliver the product to the customer, so mainly they have to spend some time or spend a lot of time to quantify in terms of the reliability of the product. When we go out to buy the product, so usually we are going to look at it in terms of how long we can use the product, and the common information we can get. They give you like the lifetime for the product, maybe 10 years or maybe 20 years. So that is very common information we can get as a customer. Now the question is, where does number coming from? So engineer in particular for the reliability quality control, engineer spend some time to collect the data and then to quantify the quality of the product. And of course, if we cannot, the reliability engineer cannot quantify the quality of the product without the data. So the data collection very crucial. And I believe I'm not going to forget about in terms of the data collection process, but I believe for this conference here, there are many talks also going to look into it, and this got a lot in terms of the data mining, data information, and intelligence, and so on. But this is very crucial and very important for the many ongoing research. And nowadays the people are talking about the data and cloud computing. So that is very hot subject. If many of you are graduate students and looking for some of the research topics, so I think this is very interesting to work on. But in order to quantify for the quality of the product, And many times, or if you are going to look at it in terms of how you can compare one model to another or one product to another, so you have to have a criteria, because of different people, different criteria, you may come up with a different product or different methodology. Okay. And this is after you qualify for the quality of the product, so going to deliver to the customer and so on. So here I'm going to discuss about some of the environment we can control and some of the environment we cannot control. So, for example, here in terms of the testing environment during development process, so many times before the product going to be delivered to the customer, so that the engineer going to spend some time to do testing and so on, and usually this is the environment you can control or manufacturer or developer can control. However, when the product available and the customer buy the product, and given today global competition and so on, so the product available, everyone from any place can buy. And we are going to look so for the operating environment here, many times we cannot control. Now the question is how relate from the testing environment here, the control environment, we can relate to the uncertainty environment, and particularly in the operating environment. So in this research and the remaining of the talk, I'm going to discuss about some of the methodology. How can we relate? How can we link from the testing control environment into the uncertainty of the operating environment? Okay. And given that, so we are going to look in terms of system ability. So mainly what is the difference between the reliability and system ability? So I know something. So this is. I know if some of you are not in reliable engineering, so this is some of the definition also including. And in here, the remaining at the top, when I say the testing environment, consider as a control environment, and operating environment consider as a random the uncertainty, because we cannot control. And given for this problem here, we are going to introduce a random variable to represent the operating environment. So this is the random variable here we consider as the error, and this error here considered as a random variable. Let's say for the given the density function to represent the operating environment, and in terms of the definition of the reliability, so that is how we define. So in terms of the probability a system is still operating at the time t. So if we are going to look at any product, any system, and we want to know if the product I'm going to want to give for 5 years, so how reliability in terms of the product going to give you. In terms of the system ability here, we are going to, beside the reliability function, we are going to including the uncertainty of the operating environment. So from the previous slide, we are talking about introduce one of the random variable error going to represent the operating environment. So this is the definition we are going to use for the system ability function. And again, system ability function here in terms we are going to introduce the uncertainty of the operating environment into the product. Okay. And as you can see, depend on the random variable error here. So this function is not very consider a little bit more complicated when we are going to quantify in terms of reliability. So if we have the random variable data here to again represent the operating environment, and if this is the gamma distribution, and given the gamma density function here, we can get the system ability function in the closed form. And in this function here, we can have in terms of the alpha and beta to represent from the operating environment, so that we can use this closed form here to determine. Let me give you one example here in terms of the system. We have a 5 component, and in order for the system to function, so we define 3 out of 5 system. Mainly, you need to have a minimum of 3 in order for the system to function. And if for the individual component, for the Weibull distribution function, and for the Weibull distribution function here, and for gamma going to represent the operating environment for the alpha and beta, so we can get this closed form solution in terms of system ability function. And to show the difference from the reliability and system ability function here, when we have the gamma distribution with the alpha equal 2 and beta equal 3. So in this case here, we can see the blue curve going to represent in terms of the product in the operating environment, usually going to give you a better in terms of the quality of the product. Okay, but if for the alpha equal 2 and beta equal 1 come from the gamma operating environment, so for the alpha equal 2 and beta equal 1 here, the quality of the product usually going to give you a lower in terms of the operating environment. So in this case here, very important to determine, to collect the data in order to determine for alpha and beta. So for the previous definition, if you recall, come from the definition. So usually we have a double integral, and many times it takes some time to determine or calculate the system ability function. So in this in this research here, we also going to look at how can we quickly come up with a solution in terms of the product in operating environment. And there are two motives why we consider in this one. Sometimes because we cannot collect the data in the operating environment. However, we can have some information because the data very important. Many times if you have the wrong data. So whatever, if you have the right model, so the gap it in, gap it out. So that is very common. We can see in the data information and data mining, and this quality of the product is also the same way, because we cannot quantify the reliability of the product without any the data. Sure. So given for the two motives, the first one is we consider what if we cannot collect the information in the operating environment. And many times even though we may not be able to have the data, but we can have some idea about, for example, if the same product, what I'm going to use in America and I'm going to use in Malaysia. So one of the examples we can see is in terms of the temperature and the environment is different. Even though the same product, but a different environment, different temperature, for example, so that it may not during the development process, so the engineer may not embed such kind of the temperature condition into the product. Yeah? So, but in order for in terms of the data collection. So even though we may not be able to collect the data in operating environment, but we may have some idea about in terms of the mean. So usually we can say, usually in the summertime, so very, very hot, and certain temperature, for example. So given for such information, so we are going to look at how we can quickly come up some of the approximation in terms of the system ability function we have. And again, when I'm talking about the reliability here, this is going to represent in terms of the control environment we have, and the system ability here in terms of the uncertainty of the operating environment. So for the previous slide, so this is the definition we have in terms of the system ability function, and we can write down in terms of the expected function of this one here. Now we are going to, I'm not going to go through for the next two slides, mainly using the Taylor series, and Taylor series is very, very common and so on. So that is going to have, and this is the result. So mainly this is the result on the right hand side here. So this is going to represent in terms of the system ability function. And this function here we can see only this is the notation, the mean going to represent the mean come from the operating environment. And the sigma square here going to represent the variance. So let's say, for example, in terms of the product going to yield in Malaysia, for example. I'm not an expert in terms of the temperature here, but you can say, well, usually this time of the year the temperature may be like 87 Fahrenheit. And the variance may be vary from day to day, from week to week, but maybe the variance may be 5 or maybe 7 or something. So such kind of the information we can get, or we can find out. Okay? So for this approximation here, this is the two information here that are the only information you need to in order to determine the system ability function here. So for the next few slides, I'm going to give some of the example come from the two common distribution, and the first one here in terms of the Weibull distribution. And the Weibull distribution, let's say if we have a system going to represent the Weibull distribution, and this function here going to have the two parameters alpha and gamma. And also we have the same eta here going to represent the operating environment. And operating environment again for the gamma distribution in order to get the closed form solution. So the traditional reliability function here very, very easy we can get, because if you are going to take the integral come from the Weibull distribution function. And this is going to represent in terms of the Weibull distribution. So if some of you are not familiar with the Weibull distribution, so this is very, very common distribution in the applied statistics for reliability and quality engineering. So this is represent in terms of depend on the parameter alpha in terms of the lambda and gamma here, so we can see the curve going to represent. The function number two, so this is the exact system ability function, and the function number three, so this is the approximation. So for the next few slides here, I'm going to show some of the examples to see what are the difference if for the product we are not going to consider the operating environment, and also the last function here going to represent, because this is the approximation, and the approximation here how far or how much error compared to the function number two, because the function number two is this is the exact solution. If you from far away you may not see, but let's see for a given from the operating environment, and again from gamma distribution with the alpha equal 3 and beta equal 4. And the last column here I want to show, so this is going to represent in terms of how much error in terms of the approximation come from the system ability function and the exact solution. And the last column here, going to represent mainly the approximation, the function number 3 I showed you, that is going to give good enough. Mainly the error almost 0%. So this is very good in terms of the research because the system ability function approximation. So easy to apply and very simple in terms of the calculation. And some of the figure here I'm going to discuss about in terms of for different in terms of the alpha and beta come from the operating environment. And if we have the alpha and beta for the gamma distribution with the 3 and 4, we can see that this curve going to represent in terms of the probability for the product going to yield in the operating environment. Usually, going to give you a better in terms of the quality compared to the control environment or testing environment. But for this one here, when the variable here alpha and beta they are the same 4 and 4, we can see in this case here it doesn't matter you are going to consider in terms of the operating environment or the control testing environment. So the result, the quality of the product is going to give you the same. And another for when we consider the alpha and beta, again, alpha and beta come from the gamma, come from the gamma distribution, going to represent the operating environment. And if the variable alpha and beta corresponding 4 and 3, so in this case here, the probability for the product going to yield in the operating environment usually going to give you less compared to the testing environment. So in this case here, this is very crucial, and we have to identify, because if this is the case, so many times when we see the product, say we can use the product, let's say for 5 years, but in reality, in the operating environment here, we may not be able to use for 5 years, but a lot less. So this is very crucial in terms of how can we collect the data in terms of the operating environment and going to apply for this model. Another distribution here called the log distribution, and this is the log distribution here going to give the failure rate function. And again, we have a 2 parameter for this function a and b. And again, for the operating environment, we are going to give for the gamma distribution. Now you can say, well, why all the time you are going to consider only gamma distribution in the operating environment? Mainly because come from the definition, we can use any function. We don't have to use in particular gamma function. However, if we are going to use the gamma function, so the system ability function, we can have a closed form, but not limited for the gamma distribution. And in this case here, we can see again for the reliability function going to give you in this form. One of the very nice behavior of the log function here. If we can see the curve from the beginning very high, but slowly down, and then moving up due to the time go by. So mainly because if we are going to look at many times for the new product, and very easy for the people going to make mistake. But after some time, the customer get used to with the product. So likely the probability you are that so the product going to fail will be less. Okay. So this is a very special function to represent. But also we can see this function here can be used in many other applications. And one of the example we can consider as a human being. So when the new baby born, so very easy, very crucial from the beginning, and something wrong, something may happen, and the baby easily to die. But after surviving after a few days or after a few weeks, so the failure rate going to go down. And of course, this is going later on because of the people going to get older and so on. So this is function very helpful and can be used in many applications. So given for the log distribution here, we can plug in into the definition of the system ability function, and then we can get this is the function number 2, mainly the exact system ability function going to consider the operating environment, and the last function here, number 3, consider in terms of approximation. So this one here for the gamma variable with the alpha equal 3 and beta equal 2. So in this case here, we can see the rest curve going to represent the system ability function. And in this case here, we can see the probability for the product going to survive in the operating environment much less compared in terms of the control testing environment. So in this case here, come from the manufacturer, we want to avoid, again, come from the manufacturer, we want to avoid this case, mainly because if you say the product can be used for 5 years, but in this case here, in reality, the product may not be well going to use for the 5 years or much less. So this example here will give you some of the analysis going to see what if we have a different variable come from the operating gamma distribution with the alpha and beta. This slide here going to discuss about because what if you cannot collect the data in the operating environment? And one of the two motives when we do the approximation is because if we cannot collect the data and we cannot determine the distribution, however we can predict or we can get the mean of the operating environment and the variance. So if this is the case, so let's say the mean of the operating environment going to give like 0.5 and the variance equal 2. So this kind of the information we can get come from the common operating environment. So if this is the case, so we can see the probability for the product going to you in the operating environment much higher compared to in terms of the reliability within the control environment. So in this case, but for the mean equal 1 and the variance equal 1 come from the operating environment. So we can see again this is the product going to survive much last longer in the operating environment compared to the control environment. And for this one here, we can see for the variance and the mean. So this is we can see in terms of the product going to survive a lot more reliable compared to in the control environment. And I'm going to skip some of this one here, but this is very important here in terms of if we have the mean greater than 1. So if the mean greater than 1 and the variance also greater than 1 here, I'd like to show you one of this slide here. Because I come come from the theoretical point of view. So in this case here, when we have the mean equal 1.1 and the variance equal 1.5. So in this case here, the probability for the product going to survive is higher than in terms of the operating environment, but in terms of the theoretical point of view. So this curve, the rest curve here should be much less. So this is still under the investigation why this is why in terms of the figure going to show it in this way. I'm going to show you one of the applications. And this example here in terms of we have a camera system going to monitor the traffic, and this is very, very common in America. So mainly the camera going to looking at it when the red light turn on, and if any car come into the intersection, so that means the camera going to take the picture and send the ticket to home in any particular customer, and then mainly the customer have no way but have to pay the money. And this is very, very common in America. So I'm going to give you this example here in New Jersey. In New Jersey, they have about 85 camera systems for the whole state. And this is one example in one of the intersections for the 1 year from May 2011 until April in 2012. Within 1 year, they sent out 17,529 tickets to the customer. So this is only one intersection out of the 85. And because of course, if you get the 17,529 and you multiply, because each ticket they have to pay $75. So if you multiply this one here, so the state government going to collect more than $1 million. So of course the state very, very happy, but many customers not happy about, in particular for the 17,549 customers. So because of this one here, people complain about why the camera system may not behave well, because if they stop in the intersection and they still get a ticket. So recently, they have some investigation, and because some of the traffic due to in the morning or in the afternoon, because if the road have a lot of traffic in the morning or in the afternoon, so they should allow more time in the yellow light in terms of some of the traffic using the street. So given for this application here, we have some information come from the state, and going to look in terms of using for the operating environment for this example, for this research here. And we're looking at, in this case here, for the mean and the variance. If the mean equal 1 and the variance equal 0.3 come from the log distribution, come at the data we received from the state. And I just want to show this one here to show in terms of for given this kind of data, so the probability for the product going to yield in particular intersection, the camera system here going to give a larger or higher than in terms of the control environment. And this example here, going to show when we have the mean equal greater than 1, so we can see that the system of the function going to give you much lower, and so on. Okay, and due to the time, I believe that in this research here, we try to look in terms of when the product going to yield in the operating environment, and many times because in the operating environment we cannot control. And when the manufacturer or developer going to produce a new product, and we may not be able to include in the design process or the environment. So now, in order to quantify the quality of the product, how can we embed some of the control, some of the uncertainty control environment into the product we are going to develop? And again, thank you very much for your question.
So, thank you, Professor Huang. So, I will allow one question from the audience. If you have any, yes, please, Professor Omar.
As you know, in Japan, the Boeing 787 now stop because there are many trouble. And so in that case, you have joined the 777 design. So what is the weak point? Can you predict by your theory such an accident? Basically, the battery was melted down or like that. Do you know the accident of 787?
Yes, thank you. As I think, as many of us already know, because the new model 787, and particularly in Japan Airlines, so have recently, for the last couple of months, have some issue about, in particular for the battery and so on. So I believe Boeing. I don't know because we're no longer working for the Boeing. But I believe that in the Boeing and also the FAA in America also having spent a lot of time to investigate what is the problem, and believe it or not, every time when the customer, in particular for the airline, have the problem, Boeing, they spend a lot of time. I can say they spend 24 hours a day to working on it. And particularly because of this kind of product, very, very crucial. And the last few months, they have been talking a lot. So I'm sure within the organization, they do try to investigate. But I think some good news research for the last couple of weeks. I believe they identify what is the problem, and hopefully they can get the government FAA from United States going to approve, because surely they decide to stop the 787, but until the FAA from United States they approve, then they can allow to fly again. But otherwise the Boeing or the airline they cannot continue for the operation. But I'm sure with the Boeing they do spend whatever the time they can in order to satisfy with the customer. So again, thank you.
Thank you. So thank you, Professor Wang. I know you're no longer in Boeing. Alright, so I would have to stop this session for Q&A because we have a parallel session start at 10 o'clock. Right? So, as appreciation to Professor Huang, I would like to invite Dr. Muhammad Syukur to accompany Professor Dr. Ali Slamet to come forward and presenting a token from the organizer. Please.